So hello everyone, good evening. My name is Damaskinos Konioris, and I would like to talk to you about our work in the computational investigation of the atmospheric boundary layer in the GABLS benchmark problem using the high order spectral element CFD code NekRS. So the atmospheric boundary layer is the lowest layer of the atmosphere, basically connects the Earth's surface with the free atmosphere. Its thickness typically ranges from 100 meters to 2 kilometers, excuse me. And the flows inside it have Reynolds numbers up to 10 to the power of 8. So we're talking about extremely turbulent flows. And the ABL is very important for a lot of scientific applications, but mainly meteorology, wind energy production, and pollutant and aerosol dispersion in, for example, cities. Some benchmark cases have been created to study the ABL and also study the flow and simulation parameters and how they affect the results, and to also test LES models. So as I mentioned, we are talking about very high Reynolds numbers, so it's almost prohibitive in a sense to use DNS, and that's why we're led to LES. And also, we are talking about a huge length scales, so we have a vast physical dimensions, and that leads to very high number of total grid points, which of course leads to a computational cost that is very high. That can be dealt with the use of HPCs and their parallel computing capabilities, alongside, of course, the acceleration that GPUs offer to speed up solutions. And that is why we are using the CFD code NekRS. So NekRS, as mentioned previously, is an open source, high order spectral element CFD code. You can find it if you're interested in the GitHub link I have provided. The version that we used, which is the current version, is the V23. It is based on its predecessor, NEC 5000, which is a traditional CPU-only CFD code. So the main advantage that NekRS has is the utilization of the GPU acceleration. It has been tested on various well-known HPC architectures such as Summit or Crusher, and has shown great performance and scaling behavior. So what we are aiming for in our work is to simulate the ABL benchmark case called GABLS, which I'll explain in a moment, to verify the results with its predecessor, NEC 5000, to also test NekRS's capabilities on new HPC architectures. And one way to do that is to perform grid convergence analysis for our problem, which basically means push NekRS to its limits by continuously raising the resolution of the problem, and to also test NekRS's scaling performance in terms of parallel efficiency and scalability. So the benchmark case that we studied, the GABLS case, it's about an ideal night cycle. So basically a stably stratified flow, which means that the higher we go in height, the potential temperature or the temperature raises. The Reynolds number for our case is about 50 million. The control volume, the computational domain dimensions of our case, is basically a cube with a side length of 400 meters. The latitude for our case is 73 degrees, which affects the Coriolis parameters and the Coriolis force. We have a geostrophic wind, if you can see there, in the X direction, a constant geostrophic wind that drives the flow of 8 meters per second. We have initial temperature distribution, as you can see in this image, of 265 kelvins up to 100 meters, and then it increases by 0.01 kelvins per meter up to the top of the domain. We also have a wall roughness at the bottom boundary, which is basically the Earth's surface or the ground surface. And the total simulation time is 9 hours. And here you can see the final horizontal velocity distributions for W and U at the end of the simulation. And also the height of the low-level jet, which is basically where the horizontal wind speed peaks, and also the boundary layer height for these examples. Now on to the computational domain, which, as I mentioned, is a cube of with a side length of 400 meters in each dimension. For the lateral sides of the cube, we have periodic boundary conditions. For the ground surface, we have a traction boundary condition for the velocity, according to Monino book of similarity theory, and the zero normal to the ground velocity component. And the flux boundary condition for the temperature with a constant surface cooling rate of 0.25 kelvins per hour, which means that the ground is constantly getting cooler and cooler. And for the top boundary, we have a Dirichlet boundary condition to match with the geostrophic wind of 8 meters per second and an adiabatic wall for the temperature. So the simulations that we ran had the grid resolution that you can see here. So from 128 cubed to 2048 cubed total number of grid points. And that last one is approximately 8.5 billion grid points, so extremely high. And on the right, you can see the number of GPUs that we used for each of those cases. The production runs were performed on the GEOS booster machine using AMD EPIC CPUs and NVIDIA A100 GPUs. Now on to the maths of the problem, the governing equations. We first have the Navier-Stokes momentum equation and the energy equation. The momentum equation has a Coriolis term and the buoyancy term. And the LES method mainly focuses on the stress terms, which have a part based on the result scales, which are denoted by an overbar, and the part based on the subgrid scale, or a subgrid scale part, which is denoted by the symbol SGS. And that's where our the LES model that we used comes into play. We chose to use a mean field eddy viscosity model for the anisotropic part, and then Smagorinsky model for the isotropic part of the SGS stresses. Moving on to the results, here we can see a comparison of the velocity and temperature distributions at the time average during the 8 and 9 hours of the simulations. Here we can see the 512 cubed case, but these comparisons were made all the way up to the 1024 cubed case. And as we can see, and as well in all the instances, the results were on top of each other, which of course verifies the results of NekRS and allows us to continue on with our work. Here we can see the development of the boundary layer throughout the now 9 hours of the simulation for the different grid resolutions. And we can see as we go further in fidelity, as we go higher in resolution, the turbulence effects are getting obviously more clear and more well depicted. The scale being shown here is the horizontal wind speed. And at the end of the simulation, we can see at the top of the really dark blue area, the boundary layer height. And also here, some horizontal slices of the computational domain at the height of 100 meters at the 6th hour of simulation for the different grid resolutions that we simulated. And I think here the increase in detail in depicting the turbulence effects is even more clear than previously. Next, we have the grid convergence analysis that we performed. On the left, we can see the velocity profiles for the different resolutions that we simulated. And on the right, we have a bar plot that shows the mean error of each of the smallest resolutions compared to the largest case. And the results indicate an asymptotic convergence by increasing the resolution, of course. And I want to say that the simulation of the 2048 cubed, so the largest case, was not previously possible with NEC 5000, and that was only made possible and achievable by the use of NekRS on the HPC architecture. Next on, we have the scaling results. First, we take a look at some GPU scaling results. On the left for a strong scaling and on the right for a weak scaling analysis. We we can see comparing, these results are for our simulations on two machines, the Juice Booster, which uses NVIDIA A100, and on Summit, which uses NVIDIA V100. And as we can see, the performance on the NVIDIA A100 is about 1.5 times better than the performance on the V100, which is proportional to the bandwidth memory improvement that the A100 have compared to the previous generation NVIDIA cards. We can also notice that we have near ideal parallel efficiency until about 2.5 million grid points per GPU, which seems to be the strong scaling limit for this case, because below that, the parallel efficiency drops under 80%. Last but not least, we have the CPU scaling results. With the blue line, we can see the performance of NEC 5000 for the 512 cube case. With the red line, we have the performance of NekRS on the same CPUs as NEC 5000 in the same case. And for a reference, we have with the black line the performance of NekRS using GPUs. These simulations were run on LumiG. And we can see that by comparing the blue and the red line, that NekRS is about 2.5 times faster than NEC 5000 on the same exact case with the same exact CPUs. But also, more importantly, that by comparing the black and the red line, that NekRS on GPUs is significantly faster, which resulted in about 60 to 70 times less node hours required on GPUs than on CPUs. In summary, we studied the GABLS benchmark case. We simulated this case for various resolutions, both on NEC 5000, which is traditionally CPU-only CFD code, and on NekRS, which uses GPU acceleration. We were able to verify the results on NekRS compared to the NEC 5000 results, which allowed us to proceed with our work. Then we performed the grid convergence analysis on our problem up to a resolution of 2048 cube total number of grid points, which was only possible through the use of NekRS, and an asymptotic convergence was achieved. Then we wanted to evaluate the performance of NekRS, and that is why we ran these cases on various HPC machines. And the results indicated that the performance improvement of NekRS is pretty much analogous to the memory bandwidth improvement of the GPUs that we utilize for each case. We also saw that we have near ideal parallel efficiency until about 2.5 million grid points per GPU, which seemed to be the strong scaling limit, because beyond that point, the parallel efficiency dropped significantly. And also that NekRS was about 2.5 times faster than NEC 5000, which on the same case with the same CPUs. But the most important, I think, that the fact that NekRS utilized 60 to 70 times less GPU node hours, also as opposed to CPU hours. I would like to say a special thanks to the Center of Excellence in Exascale CFD, to the Jülich Supercomputing Center, and to the Argonne National Laboratory for making this work possible. And thank you very much for your attention.